Hello, and welcome to this Kistler webinar. My name is Matthew, and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's session. Just to the right of the main presentation window is the speaker bio window with background information on today's presenter. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section and click Submit. Your question will be placed into the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now I would like to introduce today's presenter, Bülent Taşdelen. Bülent Taşdelen has worked in machining for 16 years, starting with a master's degree and PhD degree in metal cutting at Chalmers University of Technology in Sweden. He joined SKF Central Manufacturing Development Center in 2008, working with metal cutting machine and process development. From 2014 to 2018, he was responsible for the metal cutting R&D and implementation team, which was responsible to develop and implement new metal cutting technologies for SKF Group. The last year at SKF, before joining Kistler, he worked as Process Development Manager in the Gothenburg factory and was a member of the factory management team. Bülent, welcome to today's event, and with that, I will pass things along to you to get started.
Hello everyone, welcome to this webinar. My name is Bülent Taşdelen. I'm working as Business Development Manager at Kistler. Today I'm going to talk about machining excellence, what it means and how we can support you. And I really hope that after this webinar you will get some new insights on what machining excellence is, and you can hopefully utilize that knowledge and information in order to build your own machining excellence strategy. Let's start. The agenda is as follows. I have divided into 3 chapters. In the first chapter, I'm going to talk about the machining excellence in manufacturing, in reference to manufacturing, how to achieve machining excellence, and at the end, how we can support you. So let's start with talking about what machining excellence is. If you look to the manufacturing today, we are generating solutions in our factories. Utilizing machining is also one part of those manufacturing procedures and operations. We have data and resources as inputs to our factories. And at the end, we supply solutions, and also data is generated that can be used to support customers and stakeholders, and also measure the efficiency of both manufacturing and also the business in general. If you look to the tomorrow, of course, with the help of the amount of the data which is increasing continuously, and also the ability of handling that amount of data, the tomorrow will be a little bit different than compared to today. We will hopefully be utilizing less resources. We will be using more data as input to the manufacturing sites. We will be creating still solutions, but the amount of the data which is generated will again be larger and getting continuously bigger and bigger. So it's very important to acquire and handle the right data and data amount, and that should be also a strategical part of our machining excellence in our manufacturing. As I said, data is used today currently in manufacturing in order to understand, monitor, and improve manufacturing. So manufacturing focuses on certain key performance indicators. And often those indicators are used in order to measure the efficiency of the manufacturing itself, but also as part of the business efficiency evaluation. You can see the list here. It's from lean manufacturing. Safety, cost, quality, delivery, and the environmental impact are generally used in order to measure the efficiency of the manufacturing, and also being utilized in the daily work or daily measures in our factories. If you look to the machining excellence, that will also, of course, utilized and will be utilizing more and more data. That is the highest level of utilizing the manufacturing equipment, where the best solution with the best KPI levels up here is generated by utilizing least resources in machining equipment. So, as I said, the amount of the data is getting bigger and bigger. The sensor input is very important, and if you look to the specifically in machining, you can utilize this data from the sensors for monitoring of certain aspects. Generally, tool wear or abrasive wear control is generally utilized. You can also detect and react on machine and process abnormalities. You can also control and monitor the status of the operations, number of parts, scrap rates, delivery time, and forecasting, and so on. And of course, by monitoring, you can decrease the operator-machine ratio and dependency. And that will enable you to utilize operator for other machines, so you will decrease the cost. You can utilize that input from the sensors in order to build correlations between sinus and quality parameters. So you are indirectly measuring your quality parameters by the help of the sensors. With the data that you can get from the sensors, you can optimize your process either online via control loops, which I will mention more, or offline. So you build an understanding, you develop, and you plan your maintenance work. And of course, the data also enables you to increase the traceability. Let's now move on to how to achieve machining excellence. If you look to the step-by-step how to achieve machining excellence, the first foundation, the base of the excellence is, of course, ensuring that you have the right machine properties, you understand that, and you can optimize certain settings both mechanically and electrically. This is the base of achieving machining excellence. You can make measurements on your machines offline, in this case. You can measure the accuracy of the positioning, the stiffness, which I will mention more, both mechanically and electrically, vibrations, temperature stability. And the second step, of course, you need to apply the best process data, the settings into your process. And it can be the best cutting tool or abrasives, the geometry of such, the coatings, the topography, and so on, the cutting data, coolants, chucking, the machining strategy, how many cuts you should do, in which directions you should make your movements, and so on, because there will be differences. And so we have done the first step, the second step, but remember that you have a machine and you have tools that are wearing out during the process. So you would like to make, or you need to make compensations of such wears and being able to monitor and detect that. And at the end, when you do that monitoring and detection and control, then we are talking about intelligent machining. So you are monitoring and making compensations for the wear of the cutting tool and abrasive, and even some machine parts. You can make machine and process adjustments with that input, of course, online or offline, so that you can improve your CPKs and other KPIs. As I said, to summarize, sensors are used and should be used to monitor and detect the wear when it comes to the machine. Also, during the process, and at the end, you use this input to build your intelligence and monitoring. This is what we call machining excellence. Let's now start by talking about the base of the machining excellence pyramid, and that is the machine accuracy. Let's start with the machine accuracy measurements and a little bit understanding of machine movements. We have positioned our machine part in certain coordinates. We program it to go to B, and we expect that it will go a straight line. Of course, in the reality, it does not do. It makes some iterations and end up in a position which is as close as possible to the program position. So, and those iterations are being done at each what we call IPO cycle, input-output cycle. So the accuracy of machine positioning and holding this position under load is what we call the total stiffness. That's an important parameter. I will talk a little bit more. And that is depending on the mechanical and electrical construction of the machine. So it's very, very important to understand first the accuracy of your positioning in your manufacturing equipment. And one of the easiest way is to utilize two axes which are perpendicular to each other and perform circles. For instance, as you can see here, because you will realize that the machine is doing certain errors, and that will affect your process. So let's now talk about the effect of some of those machine errors that I mentioned, the effects on the product and of course on the machine itself. Cyclic error, as I mentioned before, you have the iteration at every IPO cycle, and those iterations, because of the mechanical and electrical construction, making some errors, as you can see in the picture here also. And of course, those type of errors will affect the surface roughness, the waviness in out of roundness, especially the medium and high band. It can cause chatter, and of course, at the end, it will decrease the tool life. We have then stick slip. As you can see, it happens when the axis will change direction. It has to brake and then accelerate, as you can see here. So, and this will of course affect the surface roughness before and after axis changing direction, the waviness again, just before and after axis changing direction, the straightness, it can cause some steps, and it's important for when you are making radiuses and curvatures and so on. And then we have backlash and reversal spikes. As you can see, we have the backlash and reversal spikes when again axis changing direction. It can be, all those errors can be mechanically and electrically caused. And those backlash and reversal spikes, of course, it will affect your dimensional accuracy, the roughness just before and after axis changing direction again. And it may cause steps on your part. Let's continue with the stiffness. As we said before, it's both static and dynamically. Especially the static stiffness will affect your dimensional accuracy. The dynamical part will affect mainly the surface roughness, the waviness, and of course both will affect the tool life at the end. Then in some cases, machine axis may have different speeds, or it can be that because of the machine aging and frictions and so on, it does not make the circle anymore. As you can see here, it's making elliptical shape depending on which direction it's making the circles. And of course, this will affect the dimensional accuracy and the straightness of your machine and at the end your part. Temperature stability, it will affect the dimensional accuracy throughout the batch. And the vibrations, of course, it will affect the dimensional accuracy at the end of the day, profile, the straightness, the roughness and also out of roundness, as we say, the waviness. And of course, at the end, the tool life or your abrasive life. And then last but not the least impact is, of course, the decreased machine life and increased maintenance costs due to those errors. So that's why it's very important to really understand what type of errors you have in your machine, which part is coming from mechanical part, which part is coming from electrical part, and how you can adjust that. Now let's talk a little bit more about the machine accuracy measurements. We have talked about the accelerometers, understanding the machine movements. One specific case, for instance, performing frequency analysis to understand the nature frequencies of your machine and process. You can do it offline and online, as we said before. We propose, for instance, to make measurements when the machine is switched off totally, so that you can capture any disturbances coming up from outside the machine, because it may have. Then you can make, for instance, moving of the slides and make measurements, rotate the spindles, make measurements, put on and off some coolants, robots, and centering equipments and so on, so that you build an understanding of what type of disturbances and frequencies are coming from what. And at the end, you make the cutting and make the online measurements so that you build an understanding. If you want to make even more a deep understanding of the deflection modes, of course, then you can utilize the hammer with the force. In this case, as we said before, you can utilize force and displacement sensors and procedures for static stiffness analysis. And the idea is here again, I want to mention, to build understanding and correlations between offline measurements and in-process measurements. That is crucial. Let's now talk about the second step in the machining excellence pyramid, and that is the process itself. We are talking about machining, different types of sensors. I will mention a little bit more, but remember that machining forces are dynamical changes. So if you look to, for instance, milling, if you can zoom, if you have the right sensor technology, you can really capture, in this case, milling with 4 inserts, really what's happening around inserts. If you look to the turning, you have both statical part, but also the dynamical part, the changes in your force fluctuations. So when you have built that, the base in the former slide, if you remember, understanding, and then on top of that you have the online measurement now, then you will have more understanding and much better chance to build monitoring and optimizing your process. The force signal here consists of information, of course, from different characteristics, properties of the machine process. The information comes from chip formation, tool wear, surface quality, dimension and roughness of the part that you are cutting, the imbalance of the spindle and workpiece system, the interrupted cuts, out of roundness of workpieces, microstructural effects you can capture with this in this case measurement. You can also see the effect of machine mechanical electrical configuration if you build understanding from step 1. For instance, from control loops, the stiffness, both dynamic and static, the resonance, and also vibrations from or characteristics from the rotor elements, the bearing elements, and so on. And also, of course, there is information also can be hidden here, coming from the external forces, coulomps, pipes, oscillations, and so on. So again, the idea is to complement your offline measurements with online machine and process measurements with the selected right insert so that you can capture the dynamic in order to build understanding, build correlations, and to enable control loops. Let's talk about a little bit the piezo technology. Since I mentioned before, it enables you to capture the high dynamic of the machine process complex system, which I have been showing. Let's have a look at this example. It's a force plate dynamometer, can measure up to 10 kilonewton. And now we are going to place an all seal, if you can see here, and make measurement. And see if we can really measure. So you can see that we have now placed the O-ring, and then we have lifted up. And if you look to the force value, you can see that with the force dynamometer that can measure up to 10 kilonewton, we can measure 0.0032 newton. So the piezo with the high sensitivity, it enables you to measure the statical part, high forces, but also the small forces with high dynamics, which is needed. Another case, if you look to those plots here, is the comparison between a piezo rotating dynamometer versus strain gauge. It's a milling operation with 4 cutting edges. You can see on the left-hand side upper corner here the torque measurement, the zoomed plot here. Each rotation is between the red lines, the same thing for torque, and then you can see it also torque around your tool with a higher accuracy and resolution with the piezo, whereas with the strain gauge, when the forces are too small, then you don't have that resolution nor the repeatability. So that is the characteristic of the piezo and the advantage of piezo, that you can capture the high dynamics. So if you make a summary of the type of the sensors here, as you can see, where the first choice is represented as the green box, the yellow means those sensor types occasionally used, the red ones, yeah, from time to time, but not wide reference. then you can capture different type of parameters. I've been talking about when it comes to the machine, deflection, correlated to the stiffness, where you can utilize force and strain sensors, vibration, also even on the linear moving axis, that is called cyclic error, as you remember I mentioned before. For instance, accelerometers can be used. And then some product quality parameters such as straightness, surface roughness, waviness, dimensional accuracy, material properties, they're all correlated to certain measurements and signals. For instance, straightness correlated to the deflection, and stiffness, and that can be measured with the force and strain, especially the static one. The material properties with acoustic emission, there are references where you can capture the microstructural changes through the batch with acoustic emission during machining. And of course, in many cases, we build our monitoring system based on the tool or abrasive or stone wear, where you can pretty much utilize all those sensors. So you need to be able to know what you're really looking for. Also, always include the machine measurements offline and online. And we can support you with the know-how. Let's go back to this pyramid again, the machining excellence pyramid. We have the first, as I said, machine accuracy and performance optimization. So what kind of sensors can be used then? You can utilize, for instance, accelerometers, which I will tell a little bit more about, to map the frequencies coming from rotary and linear axis. You can utilize hammer with force sensor to find the response function and deflection modes. You can utilize simple force and displacement sensors to measure the stiffness and deflection, of course, so that you can understand the weak joints. Or you can utilize other equipments, standard equipments, to measure positioning, since that is important, such as ball bar, the laser, and so on. And the second step in the process data, you can utilize acoustic emission sensors to optimize the NC program, acoustic emission sensors to detect certain wear types, and also acoustic emission sensors to detect material property variations. And those can be used online in the second step. Then, of course, you have force and strain sensors, which can be used to measure the certain wear types, tool deflections, and thereby optimize the NC program. Accelerometers can again be here used to measure the certain vibrations. So what you do is that you combine online and offline measurements here. And at the end, of course, in intelligent machining, what you do is that with those sensor inputs, you can build control loops, monitoring, or you can utilize those measurements in order to build a correlation between product quality parameters and those measurements. So you are some sort of utilizing that input for indirect measurement of certain quality parameters, so that you can decrease the amount of measurements, for instance. And of course, you can build your traceability register. So as I said, sensors are used to detect the wear and abnormalities in the first and second step. And in the third step, you build monitoring and control loops. Let's now talk about the last step in achieving machining excellence, and that is the intelligent machining. So I will give two examples on that. Now let's move to the last step here, if you remember, intelligent machining. So we need to make the offline measurement of your machine is the first step, online measurement during the process with the right sensor, build the correlation, and then make the control loops. In this case, the most important parameter of the product is the profile accuracy. So it's very important to keep the profile accuracy during the operation within the limits, and that is correlated to the force and deflection. So it's a machine property that is stiffness. You make the offline measurement, you know exactly what that value is, you know the quality parameter profile is connected to the force measurement, then you can connect that signal to the machine to make monitoring and also control loops. So in this case, the profile accuracy without force control is, as you can see here, but with the force control, it is much more improved. In another case, control loop in honing, the intention was to change from grinding to measurement here in two different machines to, in the same machine, make finish out turning and measurement. The part is, as you can see here, the limitations are surface roughness and cylindericity. So you need to integrate your force measurement here and build that correlation between the machine characteristic, the product quality parameters, which is important here, and then build your intelligence in order to steer your honing process in this case, so that the product quality parameters are within the limit. So integrate a force sensor to control the honing parameters online in the last step here. Now let's move on to the last chapter. How can we support you then? How can we support you as Kistler? We are offering trainings about machine evaluation and optimization, the foundation of the machining excellence. We are offering application-based trainings, turning, milling, upon request, different types of operations, trainings about our products, about signal analysis, and also customer-specific trainings, of course. We can make supervision on customized solutions for sensor integration. We can supervise projects where you would like to build monitoring and production control, and also supervision on intelligent machining with control loops with the help of the sensor inputs. And of course, we support also you with the products with a wide range of high sensitivity piezo technology. When it comes to some of the standard products for the rotary processes like milling, grinding, and honing, we have both dynamometers, stationary, and the rotary, as you can see here, 9170 and 9171. They can be used on the machine tables or on the spindles. But of course, it's more than that. Then you can also integrate different types of sensors, ring sensors when we're talking about the force here, or of course, the wireless rotating dynamometer, which is going to be released beginning of next year, that can be utilized for those operations. For turning, also some standard solutions, either on the rotary table or the revolvers or on the stationary tables. Different types of standard solutions, they are quite modular, so we are covering most of the machine adapters and the tool adapters available in the market. And of course, again, the ring sensors can be used in order to integrate those measurements in the second step. And of course, this is more than that, especially when we are talking about integration into the production equipment. As we have mentioned before, acoustic emission sensors, strain sensors, force and torque sensors can be utilized. The core is, of course, the piezo technology. Then, of course, there are some production hardware and software, also standards such as Maximus and the PTS app, which is coming up now, beginning of the next year, customized for cutting processes. Integrated solutions also are possible, integrating on the spindles. Different types of integration, as you can see, on the tools or on your machine or your robot. And as I said, the wireless solutions, which will be coming more and more, but we start with the rotating one. In this case, we can still combine the wireless solution with the high resolution of the piezo, going up in the sampling rate to 10 kilohertz, high rotations such as 16,000, and force ranges going up to 20 kilonewton. So if you summarize now, step by step, how to achieve machining excellence. Decide which key performance indicator to focus on the specific channel machine process. You have to really choose the limiting factor in that specific channel and specific machine to focus on the right requirement to start with. And then you need to take a footprint of your machine in certain aspects with the right measurement equipment. In some cases, you can mechanically and electrically optimize those settings, as I said before. You need to correlate the offline measurements, for instance, from ball bar, laser, force and deflection measurements, vibration, with the online measurements through right sensors. And those machine measurements, as I said before, positioning accuracy, stiffness, very important, the temperature stability and vibrations. And then, of course, you need to apply the best settings of the process data, including cutting tool, data, coolant, chucking, and so on. And the next step, you have to monitor the selected signals online and the product quality parameters to build understanding and reveal the correlations between machine measurements in step 1, process measurements in step 2, the product measure and the product quality parameters. Then you can move on to the next step. So you connect the signals, you can connect directly to the machine, either analog or digital. Direct connection to NC is often a simple way and enable faster loops. And at the end, you can utilize advanced programming to build monitoring and or adaptive machine control that I have shown 2 cases of. I really hope that you enjoyed the webinar, and I really also hope that you have got new insights and you can utilize this step-by-step strategy to build your own machining strategy to achieve the machining excellence. Thank you.
Thank you so much for that great presentation. And now let's get to the Q&A. We have some questions that have come in from the attendees, so we're going to move to answering those right now. At this time, if you haven't already submitted your question, you can do so by entering it in the Q&A box and clicking Submit. And we'll try to get to it before the close of the session. Okay, now for our first question. I am using Kistler accelerometers to monitor the vibration from grinding wheel and workpiece interaction. But how can I identify the process failure instances and control the machine parameters? We have a follow-up to that as well. And could you please provide some insight about monitoring the machining process, like grinding using vibration sensor and controlling the process parameters like wheel RPM or work RPM in real time? Bülent?
Yes, thank you. Yes, when it comes to the grinding, you can utilize different types of sensors, force sensors, acoustic emissions, and from time to time vibration sensors are used in order to see the abnormalities during grinding operation. And of course, this requires that you need to build up a know-how where you are defining what is normal and what is not. In terms of course, measuring with the signals in order to put up thresholds, in order to put up a window of different signal levels, both the levels but also even noise in those levels. Vibration sensors, yes, they are used from time to time, where you can, as I said before, you can see the normal footprint of the process during grinding. Then you define the vibrational level, and then afterwards, if you can see that that level is increasing or you have instant changes, then you know that there is something wrong. And if you have built this know-how, then you know what that abnormality is. So what you need to do in those cases, of course, connect the signal output from the vibration sensor through your amplifier directly to your machine. Often we prefer to connect through the fast NC input-output. And of course, you need to also ensure that that input and output connection is not really going through the PLC, because then you will lose time. We are talking about around 100 milliseconds if it's going through the PLC. If it's NC, we're talking about down to a couple of milliseconds. So when you connect that signal, analog signal, to your machine, you can actually directly work with that signal in your machine. When it comes to the vibrations and the, for instance, acoustic emission, it is also preferred when it comes to find instant changes, especially in grinding. Often you connect and utilize the RMS function, RMS value of that signal. Not always, but often. So it means that if there is an increase or sudden changes in your signal, you get that as an analog input to your NC directly in your program, where you can make the control. Afterwards, when you put those threshold values or the limits in your NC, when you have defined it in a presetting phase, then you can change feeds and RPMs and depth of cuts and so on in your NC. This is, of course, this requires, as I said, some sort of know-how building phase. Another way is, of course, trying to learn during the grinding process. So you take the reference, the first a couple of seconds or minutes during the interaction and take it as a normal vibration level, and then again work within, put some limits. For instance, if this value going up 20% or 5% during some milliseconds or during some seconds, then you have to do certain changes. This is how you can build the intelligence with the vibration sensor in grinding.
Great, thank you for that. And I'd like to remind the audience, you can now submit your question by entering it in the Q&A box and clicking submit, and we'll try to get to it before the close of the session. Okay, now for our next question. Do you offer filters for cutting force measuring devices or cutting edge K-factor research?
Yeah. So I can explain a little bit for those who are not maybe very familiar with what K-factor is. K-factor is used in order to define the form of the micro edge of the cutting tools. So sometimes you know that we have that we call waterfall. Sometimes we have symmetrical changes when we are honing our micro edge on our cutting inserts. And of course, such geometries are very important. They are there because they are affecting the limit between uncut chip thickness and while you are starting to make the chip formation. So if you take turning or milling, it doesn't matter. You decrease your chip thickness, your depth of cuts, or your feed, and then make force measurements during that time. And even if you only look to the statical value without any filtering, or by utilizing some sort of low pass filter, so because you're looking to the statical part of the force measurement, you will see that it approaches zero, but it does never go to zero. It ends up with some statical force value, and that is because you are plugging the surface. So this means that by utilizing the low pass filter and making a test procedure where you are decreasing the chip thickness, you can capture the effect of this K factor, and then you can compare different geometries on the different setups. This is how you can utilize low pass filter and force. You can also utilize high pass filter, again a force measurement, in order to see some differences between different types of K factors on your tools. Because different edge geometries does not only affect the statical plugging force, but it also affects how each edge is being worn. And that is, of course, will make a difference in the noise level of your signal. And this is how you can also utilize high pass filter, for instance, in your force measurement. So you can utilize both low pass filters and high pass filters. And in our products, both if you look to different types of dynamometers, we are having different types of natural frequencies, enabling different measurement ranges. Together with the amplifier, you are able to utilize different types and levels of low pass filters and high pass filters.
Excellent, thank you for that. Okay, moving on to our next question. What are the main steps of achieving machining excellence?
Yeah, if you remember this machining excellence pyramid that I mentioned before, it always starts by ensuring that you have the right machine characteristics. So you need to be able to measure, understand, and sometimes optimize your machines. I mean, you need to really know that your machine positions in the way that you're programming for. So positioning accuracy, and then stiffness, deflection is heart of our machining problems, as I said. So you need to be really able to measure and sometimes optimize it. So the first step is measuring and optimizing your machine. And then, of course, the second step on that pyramid, if you remember, is the process data. So you need to be able to implement and utilize your know-how, the best settings in your setup. And on the top, if you remember, we have our intelligent machining, because the tools, the machine parts, they are wearing out during the process itself. So you need to make compensations during machining and chip formation or between different parts. So these are the main steps on how you can achieve machining excellence.
Excellent. Thank you for that. Okay, now for our next question from the audience. Is there a battery needed for the wireless PZO RCD, and approximately when is it available to be purchased?
The wireless RCD is going to be released and will be available during the beginning of next year. And in that wireless RCD, we have the batteries integrated already in the dynamometer itself, so they are already there. And then you will also get the charging unit, of course. And when it is time to really exchange the batteries, we will be able to do that, offer this as a service from Keystone.
Excellent. Thank you for that. And again, I'd like to remind the audience, we have our expert online from Keystone ready to answer your questions. Please submit them now by entering it in the Q&A box and clicking submit. Okay, now for our next question. What is the effect on cost by employing intelligent machining practices?
Yeah. So if you look to the machining excellence practices, is of course, as I mentioned from the beginning, it is targeting our key performance indicators in lean manufacturing, right? We have the cost, we have the delivery, I mean the lead times, cycle times, we're talking about, we have the quality. So of course, if you are enabling your machine and utilizing your machine in the best way, so that you have the highest performance, the lowest cycle time possible from your machine, at the end of the day, you are affecting the cost effect of that machine and operation. This is one example. And the other example is, of course, the quality. If you are generating and manufacturing parts with the quality, thanks to the fact that you are applying the machining excellence pyramid, of course, at the end of the day, you will decrease your scrap rates and the cost of the scrap as well. So if you really follow this, you will realize, and you will at the end decrease your cost. This is how you do. This is the direct effect that I called. The indirect effect is of course that when you have good control on the performance and the health of your machine, you will be able to utilizing that machine during a longer life than what you can do if you do not apply the machining excellence pyramid. So in the long term, you will also save money if you are really following those steps and having control in your machine, for instance.
Excellent. Thank you for that. And our next question from the audience. Why is machine accuracy the most important step in achieving machining excellence?
As I mentioned before, when it comes to the machining excellence pyramid, the first step we put as machine. And that is because this is the manufacturing equipment where you are generating the value. You are making the value addition there in your manufacturing equipment. If the machine is really performing the operation, the movements that you are planning to do in order to produce a part, then of course you will have a better chance to get a good quality during and cost-effective cycle time. So you need to really ensure first that your machine is in good condition and it is optimized for performing the operations that you are intended to do. If you don't do that, then of course you will have long cycle times. You may have problems with the quality parameters and having high scrap rates. So really, the accuracy of the machine is almost the most important step in your machining excellence strategy and in achieving sustainable manufacturing operation with the best KPIs, as I mentioned before.
Excellent. Thanks for that. And it looks like we have one last question in the queue. So audience, please submit more if you would like. But for now, our last question, how can Kistler help us to build machining excellence?
Yeah. If you look to again the machining pyramid, imagine that my pyramid again, we're talking around that because this is very important. If you look to the first part, we have both the knowledge and the products in order to support you when it comes to the building, how I can make measurements on my machine in order to really ensure that I have the right quality. Of course, I have also mentioned products and equipments which are not really not from Kistler, but still very good to have and important to have. So that's the reason I say we have the knowledge, we have the competence, we have trainings, and we have the products, for instance, acoustic emission, for instance, vibration, for instance, strain sensors, force sensors, in order to really, measure and understand the behavior of your machine. And on top of that, we have the process data. You remember the second step you have to utilize, but you have the wear of the machine parts and tools. And again, we have different types of sensors and knowledge. Sensors, acoustic emissions, as I mentioned before, force sensors, accelerometers, and strain sensors, in order to really capture this wear abnormalities, the deflection in the machine. And if you look to the intelligent machining, it is where you are actually utilizing the input from those sensors. Then it is more than know-how and knowledge again on how to build the control loop, how to utilize the measurement chain, moving from understanding phase towards more controlling. And again, we have hardware, softwares, and our knowledge. So this is the way we can contribute in each phase, both with if we summarize, both with the knowledge itself, but also our product, hardwares and softwares.
Excellent. Thank you for that. And it looks like that was our last question, so we're going to wrap things up right there. Bülent, thank you so much for that great presentation and also taking the time to answer some questions from the audience. I'd like to also thank the audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you will be able to come back and watch it again or share it with your colleagues. Lastly, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.